Hello friends, welcome to this video on the topic performance factor analysis. I am Shomir Roy, Professor of Computer Science and Engineering at National Institute of Technical Teachers Training and Research, Kolkata. The topic performance factors analysis has been discussed in two videos. This is the first part. In this video, we will discuss the subtopics latent knowledge estimation, Bayesian knowledge tracing and performance factors analysis. After successful completion of these two videos, you will be able to explain various educational data mining, in short EDM concepts and techniques such as latent knowledge estimation, Bayesian knowledge tracing, performance factor analysis, relationship mining, correlation mining, students' interactive network analysis and so on. And take initiative to apply the aforementioned EDM techniques to technical education in our country. Let us start with latent knowledge estimation. Recently, latent knowledge estimation has gained importance in educational data mining. At the beginning of every course, it is expected that the learners already have some background knowledge of the syllabus. In order to make the learning systems efficient and to reduce frustration and boredom of the learner, this latent knowledge should be uncovered at the very outset. Estimation of a student's latent knowledge is useful for several purposes. For instance, it can be used as an input to other analysis or deciding when to proceed a learner in a curriculum or intervention in other ways. The models for estimating latent knowledge in online learning differs from the psychometric models in pen and paper tests or in computer adaptive testing, because the latent knowledge in online learning is dynamic. There are two kinds of models for latent knowledge estimation. Number one, classical psychometry. Number two, artificial intelligence in education. The classical psychometric algorithm include Bayes nets or Bayesian knowledge tracing. Situations involving multiple skills simultaneously can be handled with a logistic regression based approach called performance factors assessment. Occasionally, a combination of multiple models can be more effective for large data sets. There are many intelligent learning environments to guide the student through the learning materials. In knowledge space framework, a curriculum is presented as a graph where each node represents a test item and a directed edge between two nodes corresponds to a prerequisite relationship. A knowledge state is a subset of nodes that a learner can answer. The knowledge space is a set of all knowledge states. Given a graph, the list of knowledge states can be combinatorially decided. The goal of intelligent learning environments is to discover the latent knowledge of every learner. It tries to achieve this goal with the help of as few test items as possible and in the shortest possible time. The adjacent figure shows a simple knowledge space and its distributions. For the source of this figure, please see the e-content. Now we come to Bayesian knowledge tracing. Usually, an adaptive teaching learning system has some learner model. It is required to get an estimate of the current state of a student on the basis of data on the student's interaction with the system. This state is used to create the personalized learning environment of an adaptive system. The goal is to estimate the student's current state of knowledge as well as to predict on the basis of past performance future performances. Bayesian knowledge tracing, in short BKT, which is a special case of hidden Markov model, depicts the skill as a binary variable, that is known or unknown. Moreover, learning in BKT is presented by a transition from unknown to known state. Bayesian knowledge tracing, that is BKT, has been applied in two ways: the hidden Markov model, in short HMM form, and the knowledge tracing algorithm form. The HMM form predicts the probability that a student will correctly apply a skill when he has an opportunity to apply it. Knowledge tracing algorithm form of BKT is used to decide whether a learner has learned a skill or not. The probability of the student having learned a skill is updated whenever the student has an opportunity to apply that skill. Bayesian knowledge tracing is widely used in intelligent tutorial systems. The adjacent figure shows the BKT model along with a probable sequence of observations on the student's performance. Here, the shaded node imply hidden knowledge states. The unshaded nodes represent observation of learners' behavior, and the edges between the nodes stand for conditional dependencies. The source of this diagram is given in the e-material. Interactive learning environment ILE usually adapt to the student's state of knowledge. For instance, an ILE may contain a model syllabus consisting of the knowledge components, that is KCs, which the learners should learn, and estimate the proficiency of each learner with a KC on the basis of the learner's practice with problem concerned with the said knowledge component. Performance factor analysis, in short PFA, is a widely used model for estimating students' proficiency in such circumstances. PFA is based on linear logistic test model that exploits the student's history of success and failures while working with a certain knowledge components to predict the performance on the item currently. Learning factor analysis LFA is a starting point in educational data mining. It captures three factors influencing the learning and performance of the knowledge components. These are, for each subject, the subject ability; for each knowledge component, the knowledge component easiness; and for each knowledge component, the learning rate. Performance factor analysis is a reconfigured learning factor analysis that provides adaptive flexibility without specifying the advantages, without sacrificing the advantages of data mining, so that it can as well be used in search procedures. The standard form of PFA is given by the equation Mij belonging to KCs, n is equal to Ai plus summation over j belonging to all knowledge components, summation over beta j plus gamma j into Nij. Here M represents the accumulated learning using one or more knowledge components j of student I. The parameter beta j symbolizes the easiness of knowledge component j, and nij is the number of prior observations for student I with kc, that is knowledge component j. The parameter gamma j represents the benefit of prior practice for each knowledge component. The function used to convert m to predictions of observed probability is given by Pm is equal to 1 by 1 plus e to the power minus m. The importance of performance with respect to student learning is twofold. First, correct responses indicate that the strength is already high. Thus, a correct response gives enough reason to increase the strength estimate. Second, compared to incorrect responses, correct responses indicate better learning. However, mere sensitivity to correctness is not enough. Incorrectness should also be taken into consideration. Hence, by including both correctness and incorrectness in a model, we ensure that it is sensitive to their qualities, quantities, as well as their relative ratio. In this equation, alpha has been removed because in adaptive situation it is not available a priori. The parameter s gives the prior success of the student and f is for prior failures. Y and rho are the weighing factors. This is called performance factors analysis or PFA. It can be extended to multiple knowledge components. In that case, the betas, the gammas, the y's and the rho's are to be summed up for all j's required. So, my friends, this is the end of the first part of the two videos on the topic performance factor analysis. I hope you have enjoyed learning experience. For further details, please see the e-contents of this lesson. So, thank you very much and see you again in the next video where we shall discuss the second part of this lesson. Thank you.